Okay, hi everybody. Today I want to go over simplifying radicals, and this is supposed to be a review. This is not supposed to be a new introduction. So, taking the square root, we already should know some facts. Like we should know the square root of 1 is 1. We should know the square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. Right? Square root of 169 is 13 because 13 times 13, right? 13 times 13 is 169. We should know the square root of 81 is 9 because 9 times 9 is 81, right? So these are facts that we should not only know, but we should know them really well, right? So again, we know the square root of 9 is 3 because 3 times 3 is 9. We know the square root of 36 is 6 because 6 times 6 is 36. But what about the square root of negative 4? What could you multiply together where these were the exact same numbers that would give you a negative 4? Well, 2 times 2 is positive 4, so that doesn't work. And negative 2 times negative 2 would also be positive 4, and that doesn't work. And you can't have one of them negative and one of them positive because they have to be that you're multiplying the same number by itself. In other words, you could write this as 6 squared. You could write this as 3 squared, right? So there is no real answer. So there is no real answer. You can't take the square root of a negative number. So you cannot take the square root of a negative number. It is said to be no real answer. So it's not a no solution. It's there is no real answer or solution. There is no real one. However, so mathematicians, we can let the square root of negative 1 equal I. So they had to come up with a way to represent the square root of a negative number because it's out there in the world in mathematics. So we had to come up with how do you take the square root of a negative number? So we're going to let the square root of negative 1 be I. So, and that's called an imaginary number. So it's not real, it's imaginary. Right? So that's an imaginary number. So the square root of negative 4, so that could be written as the square root of negative 1 times 4. And then therefore we can say the square root of negative 1 times the square root of 4, that would be I, because I just told you, right? We just said that the square root of negative 1 is going to be I, and then off the square root of 4 is 2. So we're not going to write I2, we're going to write 2I. So the square root of negative 9 would be 3I. The square root of negative 49 would be 7I. So those are not real answers, those are imaginary answers. And how did we get that again? We split up the square root of negative 9 as negative 1 times 9. And then we wrote that, and if we want, we can put the square root of 9 first times the square root of negative 1. And we know the square root of 9 is 3, and we just got done saying let's let the square root of negative 1 equal I, so this would be 3I. So the square root of negative 25 is no real answer. However, there is an imaginary answer. Okay, so let's go on to the next slide. Okay, simplifying radicals. There's a lot of different ways to teach you simplifying radicals. This is the way that I like. So basically you are looking for pairs. So if we broke 8 up into the 4 times 2, and then we broke 4 up into 2 times 2, and then we still have that other 2. So here's that 2 right there. And then we broke the 4 up into 2 times 2, and that's called prime factoring. And then we have a pair of 2, so that's 2 square root 2. That's one way of looking at it. The other way you can look at it is that we could say, couldn't we stop right here? And couldn't we just, from here, couldn't we say, well, don't we already know the square root of 4 times the square root of 2? And so isn't the square root of 4 2? And so 2 square root 2. So there's a lot of different ways of looking at it. This is something you should have already simplified and done in geometry. So this should be pretty fresh. Square root of 12. So remember, our perfect squares that we should know are 1, 4, 9, 16, 25, 36, 49, right? 7 times 7, 8 times 8, 64, 9 times 9, 81. so forth, we need to make sure that there aren't any perfect squares hiding under the radical. And remember, isn't every perfect square a pair of 7s or a pair of 8s or a pair of 9s? So isn't every perfect square a pair? So this is a pair of 5s. So we can't have any perfect squares hiding under the radical. So couldn't I break 12 up into 4 times 2? Nope, sorry, 4 times 3. And then couldn't I break that up into the square root of 4 times the square root of 3? And the square root of 4 is 2, so that's 2 square root 3. Simplifying radicals. Now you could have, and with radicals there's so many different ways to do that, there isn't necessarily just one way. You could have broken 12 up into 2 times 6, and then 6 breaks up into 2 times 3, and then there's a pair of 2, so that's 2 square root 3. So you could have done it that way. I try to break mine up into factors that have one of these prime numbers or one of these perfect square numbers in it. So 32, what times what is 32? Well, 4 times 8 is 32. And then I'm going to leave that 4, and I'm not going to break it up because I already know over here is 4 times 2. And there's a pair of 4, so it's 4 square root 2. A lot of different ways to do these problems. You could have said, well, hey, so I noticed, instead of doing that, I noticed, isn't 32 16 times 2? So isn't 32 16 times 2, and isn't 16 one of those perfect square numbers? So isn't that just going to be the square root of 16 times the square root of 2? And isn't the square root of 16 4? So isn't that another way to get the same answer? Yes, there's lots of different ways of thinking through this. Square root of 6. Is there anything, right? If I break the square root of 6 up, that's 2 times 3, and those are prime numbers. And 2 is not in my list, and 3 is not in my list, so the square root of 6 is already simplified. It can't be simplified. There's no perfect squares hiding in there. There's no pairs, right? There's no pairs. There's no perfect square numbers hiding underneath the radical, so it is said to be simplified. Remember, with the square root of negative 16, isn't that 4i because of the negative number, right? Because that could be written as the square root of negative 1 times the square root of 16. Whoops, shouldn't have that double square root in there. And we can break it up. And the square root of 16, so there's your I, and there's your 4, and we usually don't write I4, we write 4i. Negative 72. So couldn't I break this up as the square root of negative 1, and then isn't 8 times 9, 72? Couldn't I break the 8 up into 4 times 2? And I don't want to break the 9 up because isn't 9 already a perfect square? So isn't 9 already a perfect square? So why would I want to break up any perfect squares? Because I already know the square root of those. So you can cross it off and say square root of 4 is 2, right? Square root of 4 is 2. Square root of 9 is 3. Square root of negative 1 is I, and so that's going to give us, with a 2 left under the radical, so our final answer is 6i square root 2. Square root of negative 11. 11 is a prime number, meaning only 1 times 11 is 11. And the square root of negative 1 is your I, square root 11. Because 11 it can't be broken down. There are no perfect square numbers hiding under the radical. So that would be our answer. 6, remember this means times, that means multiply. So 6 times, and can't 20 be written as 4 times 5? And isn't the square root of 4 2? So that 2 gets outside, and so that is 12 square root 5. So again, you should already know how to simplify radicals from geometry. So this is just a quick review of simplifying radicals. If you need more help with that, please come to after school tutoring to get some extra help with that, and we can go over it some more. Okay, multiplying. So now I want to look at multiplying. So when you're multiplying radicals, there is a rule. And the rule says that if you have the square root of a times the square root of b, that you can rewrite them all underneath one square root symbol. So you can put them all underneath one radical symbol, and vice versa. So it goes both directions. So we're going to use that rule for problem number 1. So instead of saying 5 times 10 is 50, and then breaking it down into 25 times 2, square root of 25 is 5. So 5 radical 2 is our answer. So you certainly could do that. Lots of different ways of getting there. Sometimes it's better not to actually multiply it. So sometimes it's better not to actually multiply it, because then you multiply, you get these big numbers, and you have to turn around and break it down. So sometimes what I like to do is say, I'm using the rule that says, if you're multiplying separate radicals, can't you bring it all underneath one radical? And then instead of actually multiplying it, I'm going to break 10 down into 5 times 2. And then there's a pair of 5, so that gives me 5 radical 2. I think that's smarter because it makes sense. Instead of multiplying your numbers together and getting a big number and then turning around, breaking it down, it seems smarter just to bring it all underneath and start looking for those pairs, right? Number 2, when you're multiplying, you can multiply the whole numbers, and then you can multiply the radicals. So that's going to give me 2 times 7 is outside the radicals, and then 2 times 6 is under the radicals. So obviously that's 14 outside. And then can't I rewrite 6 as 2 times 3? And then don't we have a pair of 2? So that 2 comes out as a 2 out there. So if you don't understand that, come in and get some extra help. So that's going to give us as a final answer 28 square root 3. All right, so simplifying radicals. Let's look at number 3. So let me stop this and... Okay, so you might be saying I'm going too fast. The whole point is that you can pause the video. You should stop the video. You should think it through. You should go back and rewind it and try to do some problems over again yourself. Like, that's the point of the video, is you can stop it and go fast forward and go rewind. So we are multiplying, so we've got -3, and since both of these are under the radical, because I don't want to talk too slow because the video will take a 30-minute video, right? And then the rule says we can put them all underneath one radical symbol. I could actually multiply it together and get 48, but then I have to turn around and break it down again. So I'm looking for perfect squares, and remember, perfect squares are pairs. 9 is a perfect square because it's a pair of 3s. 25 is a perfect square because it's a pair of 5s. Right? So if I break 8 down into 4 times 2, and I break 6 down into 2 times 3, isn't the square root of 4 the number 2? So I'll put that, and that gets multiplied out here. I'm running out of room. And don't I have another pair of 2's? And what I have left is under the radical, as I have just a 3, but don't forget I had a -3 out earlier from there. So whatever you pull out gets multiplied to whatever's already out there. So that's going to give me -3 times 4 is -12 square root 3 when I get done simplifying it. Again, you could have, there's a lot of different ways to do this. You could have actually multiplied them together and said -3, and then 8 times 6 is 48. And then you could say, well, isn't 16 times 3 48? And isn't the square root of 16 4? So doesn't that give me 4 times -3 square root 3? And then isn't that -12 square root 3? Sure you can. But to me, it seems silly to multiply it together and get a bigger number and then turn around and break it down. It just seems silly to me to do that. But you could have. Okay, so let's see. What about this one? So once again, we can multiply everything that's outside the radical to outside, and everything that's inside, we can bring it all underneath into one big radical. So there's my 2, and then square root, and I'm going to bring the 10, the 30, and the 9 all underneath the radical. And I'm not going to multiply it all together. That would be silly. I'm looking for pairs. So why don't I leave 10 as a 10 and break 30 up as the 3 and a 10? And I'm not going to break up the 9 because don't I already know, right? Don't I already know the square root of 9, right? And then isn't this a pair of 10s? Isn't this a pair of 10s? So I'm looking for pairs or perfect squares. So I have a pair of 10s, so that 10 gets crossed off. And that means a 10 gets out here, gets multiplied to the 2. And then isn't the square root of 9 a pair of 3's? And don't I have this extra 3 underneath, left underneath? So doesn't that have to stay? And that gives me 10 times 2 is 20 times 3, so that's 60 square root 3 when I multiply that together. Okay, so multiplying radicals. So what you could do, stop the video, go back and rewind and look at these problems and practice doing them again. Now let's look at division. Next one, division. So with division, there's a rule that says if you have a radical and you have a fraction under a radical, you are allowed to break them up in their own separate radical. You can also, if you have two separate radicals, you can also go back and put them all underneath one radical. And that only works for multiplication and division. If you have the square root of a plus the square root of b, you cannot do a plus b. That is not right. If you have the square root of a times the square root of b, you can bring them all underneath the same roof. Right? It only works for multiplication and division. Okay, so once again, there are tons of different ways of doing this. But I'm assuming you already have some skills. So I'm going through and just reviewing the basic foundation. So I'm going to use the idea that I can rewrite one big square root as two separate square roots, because that's what this rule is saying I'm allowed to do. And then isn't the square root of 16, don't I already know the square root of 16 is 4? And don't I already know the square root of 25 is 5? So isn't that going to be 4? And the square root of 25 is 5, so 4/5. Number 2. Number 2, I can take the square root and I can separate it to its own separate numerator and denominator. And don't we already know the square root of 36? So doesn't that give me 6 over the square root of 5? Right? But we're not done, because we've all agreed in the mathematical community that we would not leave a radical in the denominator. I mean, it's technically not wrong, but it's kind of like, you would never leave a fraction not reduced. Like, we just all agree that you always reduce your fractions. Because that way, if we all agree that we reduce our fractions, if I have 10 over 50 and you have 75 over 150 and I have 2/4, we don't realize these all have the same answer. And so it's hard to compare and contrast if we're not leaving everything in a simplified, reduced format. So these are things that we all agreed that we would do. So we agreed, as in the mathematical community, that we would not leave a radical in the denominator. So we have to do what's called rationalizing the denominator, because the square root of 5 is called an irrational number, and we want it to be a rational number. And I know you probably don't know those vocabulary words yet. Like, you probably don't really know what an irrational number is and what a rational number is. And that's for another time. But it's called rationalizing the denominator because right now this is called an irrational number. Right? So what we're going to do is we're going to do a trick. And this is a mathematical trick that we use a lot. We're almost like mathematicians. So isn't it true that if you multiply, so let's look at a fraction, like let's look at 1/2 for an example. If I multiply that by 4 over 4, isn't 4 over 4 just a fancy way of writing the number 1? And isn't there a rule that when you multiply 1 times any number, don't you just get that same number back? Right? So 1 times anything, don't you get it back? So 1 times 3/4, isn't that just 3/4? So when you multiply by 1, it doesn't change the number at all. So we're going to use that. That's called the multiplicative identity. And some of these properties and identities we use a lot. So really, we're just multiplying 1/2 times 1. Right? That's really just a fancy way of writing the number 1. Agreed? So when I multiply fractions, don't I multiply straight across? So 1 times 4 is 4. And 2 times 4 is 8. So 1/2 and 4/8 are exactly the same number. They just look different. So they're equal. They're equivalent statements, but they look different, but yet they really still have the same value. So I didn't change the value of 1/2. I just made it look different, right? And we did that by multiplying by 1. So the significance of that is, when I erase this, is I am going to multiply by a really cool, fancy number 1. So I'm going to multiply by the square root, I'll put it in red, by the square root of 5 over the square root of 5. When you have any number divided by itself, isn't that 1, right? 8.92 divided by 8.92 is 1. 2/3 divided by 2/3 is 1. Any number divided by itself is 1. So isn't that just a fancy way of writing the number 1? Okay, you're going to see it. You're going to see the magic. Right, so here's the magic. I'm really multiplying this fraction by 1. So I'm multiplying this fraction by a fancy way of writing 1. And I'm going to make it look different, but it's really going to have the same values. When I do that, you multiply the numerators. So we're going to multiply the numerators. So 6 times square root of 5 is just 6 square root 5. And then we're going to multiply the denominators. So square root of 5 times square root of 5. Isn't that square root of 25? And don't we know the square root of 25? Right? Square root of 25 is 5. See? No more radical. I've rationalized the denominator. The denominator no longer has a radical. So that is called rationalizing the denominator. Let's put DEN. Because 5 is called a rational number. We can go over those definitions later. So now let's test our answer. So you go way up to the top here. You cannot have any pairs underneath the radical. So is there any pairs or square roots hiding under the radical? No. Is there any radical in the denominator? No. And then could this fraction be reduced? So if 6/5 could be reduced, you should reduce it, right? So those are your checklists. You want to make sure that you check off and that these are all been approved. That's how you know you can stop. Okay, let's look at number 3. Number 3. So I'm going to erase this. So this is division of radicals, and it's really about rationalizing the denominator. So in number 3, I'm going to use the rule that says I can rewrite this as the square root of 75 over the square root of 2. Now there's a lot of different ways to do these. I noticed that square root of 75 probably has some pairs hiding in it. Isn't the square root of 25? So let's rewrite that up here. Isn't the square root, of 75? Isn't that 3 times 25, right? 3/4. And isn't the square root of 25 5? So in the numerator, I could simplify this first and pull out any pairs or perfect squares that are hiding underneath the radical. So that's going to give me 5 radical 3 in the numerator and a square root 2 in the denominator. You might think we're done, but we're not done because we say that you cannot have a radical in the denominator. So we're going to get rid of this radical in the denominator by doing what's called rationalizing the denominator. So we are going to multiply by a fancy 1, and this time we're going to use square root of 2 over square root of 2. Get that out of the way. So when we multiply fractions, don't we multiply the numerators? So when you multiply 5 radical 3 times 5 times radical 2, doesn't that give us 5 radical 6, right? Because these are both under the radical, so that's where the 6 came from. And then when you multiply denominators, when you multiply that, doesn't that give you square root of 4? And don't we know what the square root of 4 is? Isn't the square root of 4 2? And so that gives us 5 square root 6. So let's see if we're done. So let's go up to the top. Do we have any pairs or square roots hiding under the radical? Are there any pairs or square roots hiding in 6? Nope. Is there any radical in the denominator? Not anymore because we just rationalized it. Can the fraction be reduced? If so, you must reduce. So notice both of these numbers are outside the radical. So if those were reducible, you must reduce. So there you have it. We went over simplifying radicals, multiplying radicals, and some dividing radicals. If this is not sounding familiar to you at all from geometry because it's been a long time, come in and get the extra help and some extra practice.